In this video, I'm going to find the surface area of a torus, which is usually called donut. Okay, so there are two different methods to use to find the surface area. Yeah, both of them are calculus based. The first method is single variable calculus. That means the method that we are gonna learn in Calc 1. The second method is using multi-variable calculus. That means the technique from calculus 3. Okay, so you can see this is the donut or torus. Okay, so first of all, we need to find the equation of torus. Okay, so two methods to describe the torus. Okay, so first one is a surface of revolution of a curve, and the second one is using parametric equations, uh, using parametric equation. And the torus is a two-dimensional surface. So two-dimensional means we need two parameters. So we need two parameters to describe the equation. Two parameters, let's say u and v. Okay, so let's first discuss the method 1. So first, so using single variable calculus. Okay, so what is the curve when we rotate or when we revolve the curve about axis, let's say about y-axis, then you can see we can get this surface. Let me, yeah, so there is a torus right here. Yeah, so that's the torus. So I sketch this graph using GeoGebra. The okay, so let me see how we. Okay, so this one, if I put it right over there. That. Okay, so this is the circle in the XY plane. Let's say this is the XY plane. That's a circle. So if we rotate this circle about this vertical axis, we can say y-axis. So if we rotate this, so that's how we are gonna see how the torus is sketched. Yeah. So this is one variable q. Since this is a two-dimensional surface, so we need a two parameters. So here the parameter are p and q, or u and v. So one parameter kind of go around the vertical axis, and if you change the second parameter, let's say p, so there is another way we can construct a torus. So by keep the second parameter constant and change the first parameter. Yeah. So you can see if you yeah, this is the half torus, let's say the upper half of the torus, right? And you can see if I change the if I increase the parameter further, so we get a full torus. Okay, so the value of the parameter go from 0 to 2 pi. Okay, yeah, so we can think of these two parameter as a angle. Yeah, so as an angle from 0 to 2 pi. Okay, so now back to calculus. Okay, so now we have a circle. This circle. Uh, so this with the center right there, and okay, so there are two different parameters. So let's call this A. So A is a distance from origin to the center of the circle, and B is the radius of the circle. Let's call the B. The B. Okay, and if we rotate this circle about y-axis, and you can imagine that we will get the torus, right? So the torus we can think of is a surface, of revolution of this circle about y-axis. Okay, so now so let's write down the equation of this circle equation. So the center is a comma 0. So equation of circle, equation of the circle, which is x minus the x coordinate of a center, which is a, square of this, plus y minus the y coordinate of a center, which is 0, square of this, equal to square of the radius. Radius is b square. Okay, so solve this equation for y. Solve for x. Solve this equation for x. If we solve this equation for x, we get this right there. So x is equal to a plus minus square root of b square minus y square. Okay, so there is a plus minus. If you take the positive side, take plus. If we take the positive, so we get x equals a plus square root of b square minus y square. So this, so in this graph, that is the upper half. So this equation right here. So this graph is the x equals a plus b square minus y square, and the left half of the circle is, if we take the negative, a minus b square minus y square. Okay, now by using calculus 1 and this graph, I mean this left half and the right half of the circle, we are going to find the surface area of the torus. So we divide the torus into two parts. The first part is if we rotate the right half of the circle, we get the first part. So if we rotate this half circle about y-axis, and if we consider the another half, the left half of the circle, and we get the another half of the, I mean another part of the torus. Okay, so let's do first with the uh, with the part that we get when we rotate this right half circle. Okay, okay, so this right half of the circle, and if we rotate about y-axis, so we get the first part of the donut. Then the area of the resulting surface using calc 1, we get so this is the definite integral with respect to variable y. So we need to put the y. So we go from negative b to positive b. So negative b to positive b, so along the y-axis. And so we got 2 pi x times square root 1 plus square of the derivative of x with respect to y. Okay. Okay. So now we need to plug in the x value, and x prime means the derivative of x with respect to y. So that's the x prime. So if you take the derivative of this x function with respect to y over here, so we got a square root, and then that's the derivative x prime, and we want to simplify this expression inside the radical sign, so which I did right here, and that turned out to be this expression over here. Okay, so let's plug in this value right here and the value of x. So the integral is gonna be use the blue color, negative b to b 2 pi x. So x is a plus square root b square minus y square times square root of this b square over b square minus y square dy. Okay, so this is the integral with respect to y. But if you use a symmetry of this problem, so this guy right here, the function, if we call this function f of y, this is the even function. Okay, so what does that even function mean? So it means that if we substitute negative y for y, we get the same function. So f negative y is the same as f of y, right? Because in this expression, you can see there are all square terms. So y square term, and y square term. That means it's an even function. So if it's an even function, by using symmetry of the definite integral, so instead of going from negative b to b, so we go from 0 to b and multiply that by 2. So we get 2 pi a plus square root b square minus y square. And then here, if we simplify, if we take the square root of top, we get b on the top, and the square root of b square minus y square on the bottom times dy. Okay, sorry. So this is the integral that we need to evaluate. Okay, so we have this definite integral, this one. So if we factor 2 pi out, so it would be 4 pi right here, and then separate this into two integrals. So distribute this guy into this and then into this. Okay, so we got two different integrals. The first integral is the antiderivative of the first integral is arc sine or inverse sine, and that's just y. And if you do all these things, we can get this one. Okay, so this is just a surface area of the part of the torus. Okay, now let's do the second part. Okay, so if we rotate the second left half of the circle, which is shown right here. So the equation of this curve, if we take the negative sign, right? So we got that one here. So b square minus y square. Okay. So if I rotate this part over about y-axis, like that, so we get the another part of the torus. So let's do that now. Okay, so if we take this left half circle, the equation is given by this, and we rotate about y-axis, right? About y-axis. And the area of the resulting surface is this is formula, I think, from Calc 2. Calculus 2. And so plug in x value and then the value of this, which we got, which we already got. So that's x, and that's this one here. So only thing this guy is different from the previous computation is that we have a negative sign here instead of positive, right? So everything else is gonna be the same. So you can see that, and that's the final answer. Okay. So the total total surface area of the torus uh, this area from previous computation plus this area. Okay, so 2 pi, oops, let me use is 2 pi square AB plus 4 pi B from previous computation, and from this one right there 2 pi. So add them up. Oops. 2 pi square times A times B minus 4 pi B. Okay, so 4 pi B you can cancel out, and 2 pi square AB and 2 pi square AB, so they are like terms, so add them up. So you get 4 pi square AB. That is the surface area of a torus with the radius A and the radius B. So here, so we need to make sure that the outer radius, which is A, should always be greater than B. Okay. If this condition is not true, then we do not get the do not, right? So you can see this do not. So B is a radius from the center from here to the middle of the torus. That's a B. Sorry, this is A. So that's A, and the B is the radius of the torus. Yeah, so that's how we get the surface area of a torus using Calc 1 technique. That means a single variable calculus. So it means you can think of this surface area as a 4 pi square times outer radius times inner radius. Okay. Now in the second method, we are going to compute the same area by using multivariable calculus. Okay, so the second part of this video, we are gonna do how to compute the surface area of this torus using multidimensional calculus. Okay, so this is the torus, and so there are two A and B, so two constant A and B. So like before, A is uh, the radius from this center right here to the center of this torus. That's A, and B is so there is a circle over here. So B is a radius of this donut. So that's a B. Okay. So since it's a two-dimensional surface, so we need two parameters. So the parameter here are U and V. Okay. So U and V. So U goes from increases from pi 0 to 2 pi, and same is the case for V. And the parameter U and V define this X, Y, and Z. Okay, X, Y, and Z. So X, Y, Z is a point in the three dimensions. So, but each X, Y, and Z, so each of these depend on these two parameters U and V by this relation. Okay, all sine and cosine, and where this A and B are already explained in this diagram. So if we rewrite this equation in terms of vector calculus, so R is a vector that depends on the parameter U and V, x coordinate times I, and you know what I vector is, I and vector J and vector K. So these are unit vectors in the direction of three perpendicular axes. Okay, so we just plug in x value here. That's a x, and that's a y, and the one z from this parametric equation. Okay, so now by using this vector r, we are going to compute the surface. Okay, so this is the parametric equation for the torus. And if you guys want to understand why these are the equation, I would be happy to make another video how to derive this parametric equation for the torus. Now let's go and find the surface area. So this is the formula, the double integral. So D is the area A equals this double integral of this absolute value of this vector. So I'm going to explain what this vector means in a moment, times dA. So it's a double integral where D is the domain, this one. So this is a variable U. So U go from 0 to 2 pi. And in the vertical direction, it's a 2 pi. Okay, so D, the domain is actually a rectangle. rectangle. That's a V. Okay, and and so this two double vertical bar means the absolute value. I mean the length of the vector. So this guy is a vector. So how we compute this vector? This r subscript u, that means take the partial derivative of r, since r is a vector function of two variables, right? Two variables u and v. So we can compute the partial derivative of r with respect to u, and this is the partial derivative with respect to v, so which is r sub v. And this cross means this is not a ordinary multiplication. This is called the cross product, right? Cross product of two vectors. So let's first compute this cross product and then change this double integral into iterated integral. So change into iterated integral. Okay. Okay, so we need to compute the partial derivative of r with respect to u and with respect to v. So ru and rv first, and then we take the cross product. Okay, so the partial derivative of r with respect to u means yeah, so we consider the variable v is a constant, and then just take the regular derivative with respect to y. So that would be negative sine y. That sine u would be cosine u, and there is no u here, so this would be 0. And similarly, take the partial derivative with respect to b, considering u is a constant. So this guy would be derivative of cosine v with respect to v is negative sine v, and times cosine u, and then if we do the same thing, that's what I got here. So that's r sub u, and r sub v is this one. Okay, now we need to compute this. So this is the cross product, cross product of two vectors. Okay, so there are different methods to compute the cross product, but this is how I did here. Okay, so we make a 3 by 3 like finding the determinant of a 3 by 3 matrix. So it's vector I, the first row consists of vector I, vector j, vector k. Second row consists of the component of r of u, and the last row consists of functions from rv. Okay, so now we need to compute the cross product of two vectors, and so there are, as I said earlier, there are many methods, so I'm going to skip this one. Yeah, if we take the cross product, that's a vector we're gonna get, where that's this is the ith component, that's a j component, and that's a k component. If you simplify k component, we get this one. Okay, and now take the absolute value of this vector. So the absolute value in this context means the length of the vector, or the norm of the vector. So it's a square root of the length of the vector means the square root of the sum of squares of each component. That's what I did here. That's the sum of squares of each component, and if we simplify, we get this one. Okay, now let's go back to the surface area formula. Is given by this, right? This is the double integral where d, the domain or D is where the parameter u and v vary. So yeah, so D is a nice rectangle. So D is a nice rectangle. So rewriting this double integral is a iterated integral. So b, so take the constant b out. So D, so 0 to 2 pi and 0 to 2 pi, because D is a nice rectangle, right? Actually, it's a square. Yeah, so D is actually a square. So 0 to 2 pi and 0 to 2 pi. And that's the same here. And dA is du dv, or dv du, it doesn't matter. So this is a function of v only. So function of v only. So this iterated integral, so we can yeah, so we can decompose into a product of two separate integrals. This one with respect to du, with respect to dv, and then so this like calculus 1 problem. It's integral. It's an integral problem, a single variable integral problem. Yeah. So if we do that, the final answer we get this 4 pi square times a times b, which is exactly what we got when we use a single variable calculus method. That's all. Thank you very much. If you have any questions, please drop your comment or any questions down below. Thank you very much.